Okay, so the third method of heat transfer is radiation. So all bodies radiate heat based on their temperature. This is called blackbody radiation. The amount of heat radiated by a body, the power, is given by Stefan's constant, which has the symbol sigma, times the surface area of the body, so a bigger body will radiate more power, times the emissivity of a body, which is some number between 0 and 1 and is related to how close to a black body the radiation is, so how kind of ideal it is, times temperature to the power of 4. So at the moment, I'm radiating energy into the room. If we use a thermal imaging camera, we can pick up this radiation and get a thermal image of what bodies look like because of this temperature. Now, all bodies are also absorbing energy from their surroundings. So whether we're losing energy on average or gaining energy on average depends on if we're hotter or cooler than the surroundings. If we're cooler than the surroundings, then we will gain energy from the surroundings. If we're hotter than the surroundings, then we will radiate energy to the surroundings. So this brings us to, there's another formula for the net rate of energy flow from a body. So from before, we had that the energy lost by a body was given by P is equal to sigma A E T to the 4. If we want to get the net rate of heat flow from a body, we have sigma A E. Now the amount of energy it's gaining is given by the surrounding temperatures to the power of 4, and then the amount of energy it's losing is given by the temperature of the object to the power of 4. So this equation here gives us the net flow of heat energy out of a body to its surroundings caused by this temperature difference. Okay, so because this power radiated is a T to the 4 relationship, means a small change in temperature will have a big change in the amount of power. So this is why thermal imaging cameras and the thermometers which work off this mechanism are so accurate. Let's have a look at an example of using this equation now. So the question is, what is the rate at which the sun radiates energy? It has a surface temperature of 5,778 kelvins and a radius of 6.96 times 10 to the 8 meters. So to solve this problem, we're going to have to use the formula for our power radiated. So we've got P is equal to sigma A E T to the 4. So we need to work out what each of these terms is. Sigma is Stefan's constant, so it's just a constant, and it is equal to 5.67 times 10 to the minus 8 joules per second per meter squared per Kelvin to the minus 4. A is the surface area of the sun, so this is given by 4 pi r squared, and so it's equal to 4 pi times the radius squared, which is 6.96 times 10 to the 8 squared, and so putting all this into the calculator, we get 6.09 times 10 to the 18 meters squared. Now the emissivity for the sun is pretty much a perfect black body, so it actually has an emissivity of 1, and we're given the temperature in the question. So now we can substitute everything in. We've got 5.67 times 10 to the minus 8 times the surface area, 6.09 times 10 to the 18, times the emissivity, which is 1, times the temperature, 5,778 to the power of 4. So solving this on the calculator, we get 3.85 times 10 to the 26 watts. So this is a very large amount of energy radiated each second. Watts is also joules per second. So this is why we can get so much energy from solar energy. The Earth intercepts part of this energy in its orbit, so we can collect that energy and convert it into useful forms. Radiation is usually the least important of these heat transfer mechanisms, but it becomes the most important for objects such as stars, which are surrounded by a vacuum. So if they're surrounded by a vacuum, there's no method for conduction to occur, and there's also no method for convection to occur. So an object in a vacuum will lose most of its heat through radiation.